Right. So you probably have seen bits of this talk before, so I'll go for the beginning very quickly, and then I'll just focus on the cool, new, interesting bits. The main intro is just there for people who haven't seen this before. Right. Anyways, let's go. So why do we care about uncertainty? Because uncertainty is basically a primary requirement for AI. Any intelligent agent should know when it doesn't know, and it appropriately adjusts its behavior. I mean, even Socrates said, "I know that I don't know." So anything wise should know that it doesn't know. Right. Also, uncertainty is useful for enhancing the reliability of machine learning systems. Right. New people are just coming in. Cool. I'll pause.
My call worked. My call worked.
Yes. Right, so we have AI deployed in many applications, and some of them are combined with high risk. So some, medical applications, somebody can die, misdiagnose the virus, and we all turn into zombies. In financial systems, we might misdiagnose the price of Bitcoin, or in self-driving cars, we might crash. We would like to avoid these mistakes, and we can use measures of uncertainty in our behavior to increase the safety and reliability of AI. So this is why we need them. And the scenario of deployment is we have a model, it gets an input X, and it makes a prediction, and we get also measures of uncertainty in that prediction, and then we'd like to take some action on the prediction based on measures of uncertainty. So reject the prediction, accept the prediction, ask human help, human intervention, ask a human driver to take over driving, invite a human doctor, something like that. So this is the use case. Right, so where does uncertainty come from? Many of you have seen this before, so there's typically two sources, data uncertainty and knowledge uncertainty, also known as aleatoric and epistemic uncertainty, but those are posh, pretentious names, so we just call them data and knowledge uncertainty. Right, so data uncertainty is due to class overlap. Here is 3 Gaussian globs. We have a green dot, everything is fine, classes are non-overlapping, and we can easily classify the green dot as class 2. But if the classes start to overlap, then it's hard to say which class this input belongs to. It could be class 2 or 3 or 4. The features in this space correspond to many classes at the same time. So we can't resolve this uncertainty. This is unresolvable. Right, I'll talk about entropy later. Fine, I'll talk about entropy now. So the true level of data uncertainty is the entropy of the true underlying distribution which has generated the data. Obviously, we don't actually have this distribution, it just exists in nature. There's some process in nature which generates the data, and the entropy of this process is the true level of data uncertainty. But we don't have any access to that. A model trained by a maximum likelihood on this data, given sufficient data, will approximate the underlying distribution and therefore will give us a good estimate of the true level of data uncertainty. Right, back to examples. So examples again, you've seen this before probably. On the top we have distinct letters 1, 2, and 7. On the bottom we have letters 1, 2, and 7 which look like each other, and they're hard to distinguish. This is an example of data uncertainty. The final example of data uncertainty is this. We have a cat dog, and it's half cat, half dog, all nothing. We don't know what it is. Right. So that's data uncertainty. Now we'll go to knowledge uncertainty. So knowledge uncertainty comes when we have inputs which lie far away from the region of training data. This is data we haven't seen before. And because we haven't seen any data in this region, we don't know anything about this. So it could be the same class, could be class 2, but maybe the space wraps around in some interesting way and it's class 1 or 3, or maybe some new data lies there in some new unseen class 4. We don't know. So our models should be uncertain in the predictions far away from training data. A less extreme version is when we have inputs in a sparse region, right? In a region which is sparsely covered by training data. Here we may, let's say, see penguins on snow, but we don't see penguins on beaches in Argentina because we don't have that. And so whenever we see penguins on sand, our models go crazy, for example. Examples again. On the top left we have which data set? Question to the audience. Trick question. Which data set is in top left? Yes, and top right. Nice. Cool. Good.
What is it at the bottom?
And the bottom is a custom data set. Right. I like this is me in Paint. Right. So let's imagine we've trained a model on MNIST. It's digits 0 to 9. And we showed omniglot. It's letters from many different alphabets. It doesn't know that. So knowledge uncertainty. A less extreme version, say we have examples of 1s and 7s where 1 is just a single line and a 7 doesn't have a bar. And we see many 1s and 7s like that. And then in the test data, we have a 1 with a hat and a 7 with a bar. So our models may correctly give predictions, but maybe it'll confuse the 7 with the 1 now, for example. So this is another example of knowledge uncertainty in the lower case with these sparsely covered regions. So, final question. So this is a Rorschach test. What do you people see here? Anyway, just shout out. What do you see? Devil. Anything else? Turkey, right.
Vader.
What?
Vader.
You see Vader. You see, well, nice. Well, I see a demonic child with fire on his head, with wings and meditating, with floating strawberries around it. I mean, I see weird things. Anyways, we all think, so this is a weird example, and we all say different things. So this is a lead on into the future. If we have an ensemble of biological neural networks here, they'll give different predictions. And we know that you don't know what this is because you're all giving different things. If I showed you a cat, you'd all say cat. If I showed you a dog, you'd all say dog. And if I showed you a cat dog, you'd all say it's a cat dog. Right. Anyways, so in the end, we have data uncertainty, which is a known unknown. It's unresolvable, and it occurs due to class overlap. We have knowledge uncertainty, which is an unknown unknown. It occurs when we have inputs far away from training data or in regions of sparse training data. And the reason we care about talking about source of uncertainty is because the appropriate action to take based on uncertainty can depend on the source. So if you're doing active learning, there is no point in taking points with which you have high data uncertainty, but it is good to take points which you don't know anything about. And separating these two sources of uncertainty requires ensemble approaches, and I'm leaving it to that. So here's Bayes' rule. I'm sure you have all seen this before. If not, I'll be very, very surprised. Right. So you have Bayes' rule. You have prior beliefs about solutions, about explanations in the world. You have prior beliefs over your parameters. You see some dates, and they have posterior beliefs about the world. So your models sampled from the Bayesian posterior should generally agree on the training data, on the data they've seen. But because they're different hypotheses, they can disagree on data they haven't seen before. So because you've all seen cats and dogs, you should all know there's cats and dogs. But when you see Rorschach tests, you see different things due to the nature of the hypotheses that you all are. Right. So imagine we take an ensemble of models from the posterior. Obviously, we can predict using the predictive posterior by marginalizing out the parameters, by just averaging over the ensemble. This is what you use to predict classes. But if you just retain the ensemble itself, we want to have the following behavior from it. When our model knows something, we want to have a consistent ensemble with low entropy predictions in the model and in the predictive posterior. So we want the ensemble to agree and give a very confident prediction. When we have class overlap or data uncertainty, we want the ensemble to be consistent but give high entropy predictions. So that the ensemble, basically, so that the distributions over classes from each model in the ensemble are the same as the predictive posterior. This is what we want for data uncertainty. Finally, when we see a Rorschach test, or something we don't understand, we want the model to give a highly diverse set of predictions. So that the predictive posterior is high entropy because we're averaging over really diverse predictions, but the entropy of each model in the data set is low. So what we can then do is the following. If we measure the entropy of the predictive posterior, this should be high whenever we are uncertain, regardless of reason. And if we measure the average entropy of each model in the ensemble, this should only be high if we only have high data uncertainty. Now, if the ensemble is consistent, then the entropy of the predictive posterior and the average entropy will be the same, and this difference will be 0. When the ensemble is highly diverse, the entropy of the predictive posterior will be high, but the average entropy of each model will be low. So the difference will be big, and this will be a measure of ensemble diversity. Is this clear? Any questions? If you have questions about understanding, just ask right away. Don't wait until the end. Right, so no questions. You all get this. Excellent. Wouldn't expect anything else. Right, so basically, this difference is called mutual information and is a measure of ensemble diversity. A different measure of ensemble diversity, which we can consider, and which I use but I don't show here, is pairwise KL divergence. If we just take models from the ensemble and we average over all the pairwise KL divergences, we will also get a measure of ensemble diversity. For example, and in fact, there'll be an upper bound to this. Right. Anyway, so there's many different ways of making ensembles, but turns out that the empirically best way of doing ensembles is deep ensembles, as some of you here have so nicely shown. So, anyways, but the limitations of ensembles is still typically hard to guarantee their diversity, despite all the methods, and that it's computationally very expensive. You're running multiple models in parallel, even if you have good models, if a small ensemble is still m times more expensive than using a single model. So This brings me to the next point, and the next point is ensemble distribution distillation. How can we take all the cool things we have about our ensemble and compress it down to a single model in such a way that we retain all the cool benefits without really compromising anything? So, this is probably also something you've seen before. We can every discrete distribution lives on a simplex, and we can visualize our ensemble as a bunch of points on a simplex. Is this clear to everyone? It really should be. Cool, right. So, if we have a confident ensemble, it should be a bunch of tight points in one of the corners of the simplex. If we have data uncertainty, it should be a tight cluster of points in the center of the simplex. And if we have knowledge uncertainty, a diverse ensemble should just cover the entire simplex. Now, we can imagine that the ensemble's predictions, the discrete distributions which the ensemble gives, is actually a sample from a higher order distribution over output distributions, conditioned on the input and the data. This is a key step, right? And we'll just call mu m a sample from that distribution. This is a discrete distribution. This is like mu m is the predictions of a model in our ensemble for a given x, right? So, anyways, we can imagine that these are sampled from some distribution like this when we're confident, when we are data uncertain, and when we are knowledge uncertain. And we'll call this model a prior network as before, and it predicts, we will approximate this distribution over output distributions using a single neural network, and it predicts, it has the same mechanics as an ensemble. So it models a distribution of distributions, it can separate out the measures of uncertainty in the same way. So we predict the classes using the expected distribution from the prior network. We can decompose uncertainties in exactly the same way, except instead of marginalizing over parameters, we'll marginalize over the distributions from the prior network, and we get the same separation of uncertainty. So this is its mechanics. This is something it can do. The question is how to make it do this, right? So previously I talked about prior networks in the context of single model training. Here I talk about how to distill. So we all know knowledge distillation. Knowledge distillation proposed by Hinton and then also by Karatikara when they called Bayesian dark knowledge paper. Basically the idea is you have an ensemble of models, you average them together, you get the Bayesian predictive posterior of the ensemble, and then you minimize the KL divergence between the ensemble, predictive posterior, and the single model. Simple. And this is cool. You basically get almost the same accuracy as the ensemble, but in a single model. So now this is m times faster, computational gains, and it's all more robust to attacks and has numerous benefits. This is nice. But we have lost the we only captured the mean of the ensemble. We've lost information about the diversity. We've lost the ability to separate out our uncertainties like we had with the original ensemble. So the solution is ensemble distribution distillation, which is really a simple idea, which says the following. We have this ensemble, why don't we download the entire ensemble into a prior network? So we distribution distill the ensemble's predictions into a prior network such that it captures both the mean, the enhanced classification accuracy, and also measures of diversity of the ensemble. And the goal is to exactly maximally preserve all the information available to us. And this is done really, really simply. We have a model. It predicts the parameters of a Dirichlet distribution, right, which is a model defined on the simplex. We have a data set of the predictions of our ensemble. So for every x, we have m discrete distributions, and we're going to maximize the likelihood of those distributions under the Dirichlet for those inputs. Super simple. Just direct application of maximum likelihood estimation. And the results are, so here's a comparison. Here we have models, again, VGG architecture, so they're not state of the art, because this is what I did at the time. But anyways, individual models get accuracies far lower than the ensemble. The ensemble achieves the best performance, as expected. Ensemble distillation gets most of those gains, and ensemble distribution distillation typically does about the same or maybe a little better than ensemble distillation. So basically we have retained most of the computational advantage, of the accuracy advantage of the ensemble, as does ensemble distillation. So like this is a baseline sanity check that we're not doing anything worse than ensemble distillation, and it all seems to work, both for CIFAR10, CIFAR100, and Tiny ImageNet. Here we show the performance in terms of misclassification detection, in terms of prediction rejection ratio. Higher numbers are better. Yes?
So is this distilled on clean data or?
This is just distilled in the original data.
Uh-huh.
Right. Well, the story is there's some engineering bits and tricks to getting it to work correctly, which are in the paper, but they're like more engineering. They don't really change the the message of the method. Anyways, so here we're trying to show how good we are at detecting our errors, and we show that the ensemble is obviously better than. Sorry, this is a metric of misclassification detection performance, which is independent of the performance of the individual models. So we can compare them. Right. So ensembles do best. Again, no surprise there. And it turns out the ensemble distribution distillation does second best. So we do better than ensemble distillation, which is nice, or better than or equal to ensemble distillation. So it's nice. So there's something about the information about the diversity of ensembles which helps us in this task. Maybe just a little, but still helps, which is nice. Finally, we do out-of-domain input detection. We also have results for tiny ImageNet, but I didn't have enough space and couldn't be bothered to restructure the table. Anyways, but same story in all data sets, is that individual models do, well, they're the baseline. The ensemble does obviously best, typically. And it turns out that ensemble distillation does really badly. So because it doesn't have, it does about the same as individual models or sometimes worse. So there's something about the information in the diversity ensemble which is really important to this task. And this information is lost in ensemble distillation.
Have you used conventional, let's say, log likelihood for out-of-distribution detection? Because it's also conventional.
Log
Say
likelihood.
You can use something like maximum probability.
Yeah, I tried all of them. They all do worse than measures of knowledge uncertainty. So there's a big table. I have a big table which compares. I've compared different measures of uncertainty, measures of knowledge uncertainty like mutual information or expected parascale divergence or differential entropy do better than measures of total uncertainty. Do a little better in these tasks because these tasks have a low amount of data uncertainty. You know, it's CIFAR 10, CIFAR 100, and Tiny ImageNet have a typically they're low data uncertainty tasks. So the distinction isn't as valuable. And I'll show you much later in this talk where this distinction is far more valuable. But basically, the story is that here we're able to get about the same performance in out-of-distribution input detection as the ensemble using ensemble distribution distillation, and simple ensemble distillation seems to do much worse, which is surprising.
What would be the experimental design?
So you have CIFAR 10 test set compared against ELSON or Tiny ImageNet test sets, or CIFAR 100 test set for CIFAR 100 models, and we're trying to discriminate between CIFAR 100 and Tiny ImageNet or ELSON test sets. So all models have never seen those data sets. They're completely they're out of domain. They're unknown.
Mm-hmm.
So unlike the prior networks I spoke about before, which used out-of-distribution training data, there's nothing like that here.
And are there any ideas, hypotheses of why it happens? Why do you so that ensemble distillation starts performing even worse than individual?
So my sort of heuristic hypothesis is that ensemble diverse. So the reason ensemble the reason that the predicted posterior of an ensemble is high entropy for out-of-domain inputs is because we have a diverse ensemble, right? So ensemble diversity is the prime reason for high entropy.
Right.
Ensemble distillation just measures the final result, high entropy predictions, but not the reason for high entropy predictions. In ensemble distribution distillation, you force the model to understand diversity of the ensemble, and by learning about the diversity of the ensemble, you automatically learn about where you give high entropy or low entropy predicted posteriors. So information about diversity is primary to making any.
Well, this can explain why ensemble distribution distillation works better than single ensemble distillation.
Yes.
It doesn't explain why single ensemble distillation works worse than individual network. Why it is reported in the table. That seems to be strange.
My
It is.
hypothesis is if we use different metric like maximum probability, then just the ensemble distillation, conventional ensemble distillation, will be doing much better than in this table, but it's just the hypothesis. So maybe these measures are bad for distilled model, just because we
But
cannot
that's
say.
interesting. Why? What is the reason of why they're so bad?
Because we are using an entropy of no.
Another property of ensemble distribution distillation is that the ensemble distribution distilled model assumes that the ensemble is distributed as a Dirichlet, but the ensemble is not necessarily Dirichlet distributed at all. So the ensemble distribution distilled model will overestimate the diversity of the ensemble, because it'll, if you have two Gaussians and you try to approximate it using one Gaussian, you'll put the Gaussian over both. Same thing here. You have multimodal ensemble, you have a single unimodal Dirichlet, you'll stick the Dirichlet over a much wider thing. So you'll overestimate support and you'll overestimate uncertainty. So you're over uncertain compared to the ensemble. This seems to be good. While the ensemble distillation model can perfectly replicate the ensemble's performance in terms of the entropy of the particular posterior, because they're completely matched in terms of model class. There also might be something about temperature.
There should be some other factor. Okay.
And you still don't use any auto domain chaining here, right?
I did use augmentation data.
Yeah, that's fine. So how do you guarantee that ensemble distribution distillation achieves high entropy on auto distribution data?
It does.
Yeah, I see that it does.
No, but I mean, again, because the ensemble distribution distilled model is still a single model, it is still subject to the limitations of a single model. So somewhere really far away, we don't really have much guarantees. So I think it's useful to think of ensemble distribution distillation as a way to get a snapshot of the ensemble's performance in areas of interest. So for example, if you know that you have, so for example, like I think a great example is when you're memory limited. So if you have a self-driving car, you have a limited amount of memory on board, you really can't afford to use the entire ensemble. So you ensemble distribution distill, and in the regions, let's say you drive over Moscow and you have Moscow data, you can collect and distribution distill the ensemble on Moscow data. Then you'll be replicating the uncertainty performance of an ensemble here. But if you go somewhere really far away, you lose guarantees. So it's a nice way of snapshotting the ensemble in an area of interest, but because it is still a single model, somewhere far away, it still can do something really, really bad. So again, true ensembles will always be diverse, or hopefully will always be diverse in some interesting way.
Okay.
So yeah, anyways, that's ensemble distribution installation. Simple idea, and it sort of works, which is kind of cool. Now, the more cool stuff is uncertainty and structure prediction. So we've seen that ensembles work in classification performance. For classification, ensembles also work for regression, and people seem to get stuck on regression and classification or other unstructured prediction tasks. We have some input and we have some predictions where the predictions are typically unrelated. We have either one prediction or multiple predictions, but they're unrelated. What happens when we try to capture and model structured data, like text or speech? So you have some sequence of inputs x, x1 to t, where x is some images or word vectors or something, and we predict a sequence of labels y to l. And we can do this using auto-regressive models like that, which are typically modeled as a sec-to-sec model. This can be either an LSTM of some kind or a transformer model of some kind. In the experiments I have here, I have deep ensembles of transformer models, right? And they're applied to neural machine translation and sequence-to-sequence, end-to-end speech recognition. And the question is, can we use ensemble methods, can we scale ensemble methods to get meaningful estimates of uncertainty, which decompose into knowledge and data uncertainty for these large-scale, highly applied tasks? And the answer is we can, and I'll show you how. And the other thing is that, unlike before, where we just had a prediction and we had uncertainty in the prediction, here we can get uncertainty estimates at two levels. First level is at the individual token predictions, and the second is at the level of the entire sequence prediction. So what we do here is we train, as before, an ensemble of multiple transformer big or VGG transformer models, and we'll apply them as follows. First, before we discuss how to get measures of uncertainty, we have to discuss ensemble combination. So for simple models, you just average out, you multiply your model by the posterior, and you take the integral, or just do Monte Carlo approximation to the integral, and it's all fine. But for structured data, you can combine your ensemble in two different ways. So you can start with your predictive posterior, right, on the left, and you can decompose that in two ways. First is if you take the expectation over the entire prediction of the sequence, so it's an expectation of products on the top, and on the bottom is if you take the product of the individual predictive posteriors at the token levels. the product of expectations. And both are equally valid, mathematically valid ways of decomposing the Bayesian predicted posterior for an auto-regressive model. The question is, what works better? And so it's interesting. So we did the following thing. We trained a bunch of models, and so we combined the same models in two different ways. Both for NMT, here we train on English-German WMT17, English-French WMT14, transformer big, and ASR on LibriSpeech, LibriSpeech test clean, and LibriSpeech test other. And consistently, we have higher BLEU scores or lower word error rates when we combine our ensembles using a product of expectations. So both models of both combinations of the ensemble still do better than single models, but combining as a product of expectations leads to better end performance in beam search decoding. But it also gives us lower negative log likelihoods of the test data. So previously we did decoding, beam search decoding. Here we're doing teacher forcing. As in, we are feeding the correct reference context and everything else, and looking at the probability of the correct label. And turns out when we combine the ensemble as a product of expectations, we think that the test data is more likely, more probable, has a higher likelihood. Does anybody know why? Does anybody have any ideas why? Why this occurs? Because this is not obvious to me when I did this before.
Is it possible to show this Jensen inequality somehow?
No. Jensen does not work for
Is it
this.
possible to write down the mathematical expressions which correspond to product of expectation as an expectation of the product?
Yeah,
I
here.
think this is
Probably due to the multimodality of the expectation of the problem. It is maybe has too many modes.
No, I'm not sure it's more
Let us first discuss why there are two different expressions which correspond to the same left-hand parts.
Well, I think the truth is that they would correspond to different distributions over parameters. So if you have the same predicted posterior, you will have different prior distributions over model parameters, which lead to them. Or I think you could show that. I haven't actually shown that. But if you have a combination of a ensemble of models sampled from some predicted posterior, it is likely to be better one way or another. So it corresponds to different distributions over models.
So I guess that the two processes are possible. One process is when you sample network from your posterior, you predict a single label, and then what? No. Okay, so in one case, you predict the whole sequence of Y's.
Yeah.
This is a single network, and then you average the predictions given by a single network.
Yes.
Yeah.
And second, this is the second case.
Yeah.
And in the first case, at each step, for each element of the sequence, you use the result of posterior predictor, right?
Yes.
The result of ensembling.
Like token level versus sequence level, essentially.
Yes. So it's ensembling at different levels.
Yeah.
But I still don't understand why the left-hand side is the same.
Well, I
It should
mean,
be something different.
so I'm not saying that they're the same to themselves. They could correspond to different predicted posteriors.
Okay. So
So
it's
it's like-
should be different notation.
Yeah, maybe P1 and P2.
Yeah.
Right.
So the question is, what is better to use ensembling and then ensembling at element level or sequence level?
Yeah.
Right. And according to your experiments, it appears that it's better to
Ensemble at the token level.
token level.
Now
Maybe it's reasonable, yeah.
No, but I think the reason for that is because we don't have a true sequence model. We're not sampling entire word sequences. We're making
Right.
our atomic piece of model is a prediction of a token conditioned on X and Y less than L. So we have context, input, making a single prediction. This is the level of a single model, and this is where we should be
the
ensemble.
problem we are trying to solve.
Yes.
And this means that
And this is also
this is the
corresponds-
level where we should ensemble.
Yes, and also this is where we do training. So if we train our models using teacher forcing, which we did, which basically means that we have the correct context, the correct label, the correct input, the correct context, and we're predicting the correct label given the correct context, it's consistent, right? It's consistent with this. Furthermore, a single model, here, the log, what is it? Yes. So here, the log of, maximizing, so in this case, maximizing individual token probabilities is the same as maximizing the probability of the entire sentence, but not in the second case, not necessarily in the second case. And the same thing here, and the same thing when you train an individual model, when you're maximizing the probability of the entire sentence, it is the same as maximizing the probability of each token given the correct context.
Mm-hmm.
So teacher forcing. So this model corresponds to the assumptions and the scenario for training a single model in our ensemble. This does not. So this is more matched to our ensemble training situation. So it's more matched, and therefore we should use that.
I think it might be possible to see that the second case obtains better low likelihood than the first one.
We
I've
do.
seen a very similar thing before.
Yeah, we do. Sorry. Here, we do.
No, mathematically.
Oh, not always.
I've seen a very similar
So I did a really simple experiment where, it turns out the longer the sequence is, the more difference between them. So the shorter the sequence, the less difference. The longer the sequence, the more difference.
And it is reasonable because if you make an error in the first symbol, it
Yeah.
might ruin your prediction of
Yeah.
the whole sequence.
Exactly.
Sequence, yeah. And so if you're
So your model,
your
you are model averaging at the level you're making decisions in beam search decoding. So it seems to be the case that combining models at that level is more advantageous. So very cool. So this is nice. Now how can we obtain? So this is cool. Now how can we obtain measures of uncertainty at the token level using structured models? Turns out it's the same as before. So we have an ensemble of models predicting Y's. We have now an ensemble of models predicting Y's given more conditioning. So token level measures of uncertainty are the same as before. Nothing changed, right? Simple, straightforward application of ensemble methods. The question is, how can you do sequence level measures of uncertainty? And so this is what we'd ideally like to do. And the base component of this expression for knowledge uncertainty is the ability to calculate entropy. But entropy for a structure prediction model is intractable. So here you have this sum, and this bit of math shows that it's intractable, but the math is boring. We can show a picture taken from the AlphaGo presentation. I think, by the way, it's like the anniversary of AlphaGo or something. So this is from the AlphaGo presentation from DeepMind, but I think it's a great example. So here is the actual, this shows the combinatorial explosion. You have 4 steps, or 5 steps, and you have multiple different choices you can make, multiple different words you can select. And you make one choice, and then more choices open up, and more choices open up. And to calculate entropy, you will have to go through every single path in this prefix tree, which is intractable, unfortunately. Even for small sequences, for small vocabularies, when we have seriously big vocabularies like 40K, 100K vocabularies, and sequence lengths of like 20 or 30, this becomes 40K to the power of 30, some insane number, probably maybe more than the atoms in the universe. So you're screwed. You're completely screwed, and yeah. But we can, as always, use approximations, and we're going to use really, really simple and crude approximations. We're just going to approximate these as the sums of token level uncertainties. It's a really crude approximation to use. But you can show that the entropy of the predicted posterior, of the token level, of the sequence level predicted posterior, is approximately the entropy, the sum of the entropies of the sequence level, of the token levels. The expected entropy is also approximately the sum of the sequence of the token level expected entropies, and the mutual information, which is the sum or the difference of those two, is also, but can also be shown to be approximately the sum of the token level mutual informations, but under 2 conditions. The first condition is that we combine the ensemble as a product of expectations. So it turns out the product of expectations is also so there's a proof, there's a derivation which I don't show here, but there's a derivation and it's conditioned on two things. Firstly, that to obtain the predictive posterior, we use a product of expectations, which is easy to satisfy, and turns out that the product of expectations is better anyways. So it's fine. This is a condition we can satisfy. The second is that the distributions are independent of context, which is obviously wrong. This is obviously a very...
By context you mean what? X?
Sorry?
By context?
No, y less than L. So if we have... if we mask out y, it's all fine. Right. But
then it's trivial.
Yes, then it's absolutely trivial. But obviously this is an assumption which is very, very strongly violated. Unless you use non-auto-regressive machine translation, which is also a thing now. So, anyways, but in situations when we are very insensitive to context, so there are probably bits in the sentence where the context doesn't matter a lot. Or maybe the context dependence is limited. These approximations will be better. When the context dependence is very strong, these approximations will be worse. I also examine a bunch of other measures of sequence level uncertainty, which I don't talk about here, mostly because, which are based on the log scores. So something else which you can do, which I don't show here again, and maybe I really should have, is if you look at the log scores of the entire sequence, and you look at the average log score, the log score of the predictive posterior of the particular hypothesis, the average log scores, the log scores of the predictive posterior, and the pointwise mutual information, which can be seen as a measure of diversity. Anyway, so you can derive measures of diversity, which don't depend on those approximations, but they're sensitive only to a single path. They also work, but I don't talk about them here. But they work about the same, turns out. Anyways, results. So we evaluate this on 3 tasks. First is sequence level error detection, when this is for ASR and translation, and it turns out it's far easier to do this for ASR than for translation. And the reason is because turns out that ASR is a low data uncertainty task, interestingly, while translation is a high data uncertainty task in the labels, because the same sentence can be translated in very, very many different ways, but the same sound can be transcribed in exactly one correct way. So there's multiple correct translations, which is why translation is a high data uncertainty task, while speech recognition there's a single correct transcription of sound, so it's a low data uncertainty task. Anyways, but turns out we can. So this is again prediction rejection ratio and beam search decoding and measures. Again, the story is generally the same as for unstructured scalar prediction. Measures of total uncertainty are better than measures of data uncertainty, and so on and so forth. Although using the log score, so for translation, using the log scores of the predictive posterior for this particular realization seems to do a little better, or a lot better than the average entropy. Interesting. So TU is the average entropy. Data uncertainty is the average expected entropy, mutual information, and so EPKL is expected pair scale divergence. Again, we just sum the token level expected pair scale divergences. And measures of knowledge uncertainty do worse. So again, same story as before. Also measures of total uncertainty in this particular hypothesis, rather than the entropes along the hypothesis, are better because they are looking at the probability of the error made in this particular realization. So again, this is nicely consistent with unstructured uncertainty estimation, which is fine. Then I look at token level error detection, and here it is almost meaningless to do token level error detection for translation unless you have human labels of errors. So it's very difficult to automatically get correct error labels for machine translation because you have rearrangement, you have synonyms, and multiple correct. If you have a reference and you have a hypothesis, a good hypothesis, as judged by a human, can also have very low BLEU or very low overlap with your reference. So it's really hard to do token level error labeling for translation. But for ASR, you just do alignment, Levenstein alignment, and you just get the correct thing, which is nice. Anyways, here we're looking at percentage area under the precision recall curve, because this is the standard way of assessing token level error or token level confidence scores in ASR. So for ASR, token level confidence score estimation is a long and explored area. And this is the standard way of assessing that. Again, your baseline is the error rate, or the baseline recall rate. And we're much higher than the recall rate. Again, measures of total uncertainty are better. So again, consistent with simple unstructured prediction. Next, we go to auto-distribution. So no questions here? All fine? Cool. Next, we get to the more fun stuff. So this is auto-distribution input detection for speech recognition. Here we have the in-domain dataset is either LibriSpeech test clean or LibriSpeech test out. AMI eval is a different. So LibriSpeech is English read books. Somebody is reading stories in books. LibriSpeech. Test clean is a cleaner, nicer subset. Test other has more noise, which has a higher error rate. AMI is English meeting transcription, spoken meeting transcription dataset. AMI eval. So it has a different. Sorry.
Meeting transcription. You mean?
So somebody's having yes. So LibriSpeech is read data. AMI is spoken, like conversational data.
Okay.
And then we also took French and Russian data from the Common Voice project. So this is a different language altogether. So we can detect, so using measures of total uncertainty, we can detect, we can nicely separate between, sorry? Any? No. Right, we can nicely separate between LibriSpeech test other, which is noisier than LibriSpeech test clean. We can generally separate them out, which is nice. If you give it meeting, like really mismatched English, conversational English versus read English, we can discriminate them even better. Although again, it seems to be mostly based on data uncertainty. And finally, if you give it a different language, you can just see that it's a different language altogether. So it turns out that auto-distribution input detection seems to be very easy for speech. And one of the reasons is that you have a very highly informative signal going in. You have the original speech signal going in, and it has a lot of information. Background noise, speaker voice, speaker rate, speaker gender, speaker age. It's a very informatively rich information going into your model. It's very easy for the model to see differences between background conditions, noise conditions, voice conditions, and so on and so forth. So this is nice. It's nice that it just works. And this is using an ensemble of just 4 models. Although this is already really expensive. Now, for translation, things get far more interesting. For translation, you only have the sequence of of byte pair encoding tokens going into your model. So your model needs to be able to tell apart the structure of token sequences. It's far more challenging than by looking at a really rich speech signal. So we trained our model on WMT17. This is English-German, which is parliamentary stuff, Europarl, I think Wikipedia stuff, Common Crawl, so lots of internet. So it's a really wide domain stuff. And our dataset, our test dataset is news test. So it's a news dataset. And we took a medical dataset initially to just look at different. So this is English-German, English-German, and we're trying to separate out whether we can detect different domains. Turns out separating out medical domain from the news domain is very difficult because presumably both news and medical is in the training data. So they're both basically in domain. But maybe the medical is a little less in domain because measures of knowledge uncertainty do help us. Using measures of total uncertainty, we just can't separate out. They're both valid English. We can't separate them out. But knowledge uncertainty sort of helps, especially expected pair scale in this case. When we give it LibriSpeech English data, so this is now read English data, so spoken English data versus written English data. There's, so spoken language and written language has a very big structural mismatch. And we can detect that much better than we can the medical domain mismatch. And again, measures of knowledge uncertainty really help here. Finally, we just did a noise experiment. We took the news test data and we permuted the order of the symbols in the text.
So knowledge uncertainty means that our ensembles
are diverse. Yes. Knowledge uncertainty means ensemble diversity. Right. So for permuted data, we just took news test inputs, source text, and we randomized the order of the tokens, just to see whether we can detect really, really noisy, random, meaningless English token speech. And turns out we can detect that really well using total uncertainty, but even better, almost perfectly using knowledge uncertainty. But again, nothing too surprising here. The really surprising stuff comes when you feed in different languages. So I gave a English-German system German as the input rather than English, or French as the input rather than English. And in this situation, the models exhibit very confident copy through. The models just copy the input to the output really confidently. They copy much more confidently than they decode news test. Therefore, our ROC AUCs are less than 50. We're more confident in the out-of-the-domain data than we are in the in-domain data. Because of this, because we are much more confident in how we copy input to output than in generating a valid hypothesis.
But what was the pair of languages?
So the model was trained on English to German,
English to German.
and I gave it German input. So
And if you give it French input?
same. French input, English. Sorry, the model is English German. I gave it German input or French input.
For English German model.
Yeah. So
input.
yes.
But then it can copy, right?
No, but you can BP tokenize it. BP tokens can be quite general. You can transcribe. So BP tokens are subword token units. And you can learn a wide enough vocabulary to cover most European languages. You also have out-of-domain tokens.
What about the accuracy of the?
Oh, sorry.
The accuracy.
Well,
of the translation.
it doesn't translate anything. Sorry, for here it doesn't do anything.
Yeah, but
Like it's zero accuracy translations.
so it copies like.
Almost perfectly. It almost perfectly copies. But almost perfectly copying means the ensembles are diverse, and measures of ensemble diversity are much better at detecting different languages. So here is a great example where separating out your measures of uncertainty is not just a little better, but like the difference between epic failure and it working.
Wait, I still don't understand. If they simply copy the input, why should they
There's
use error?
still some noise in the input. Sorry, they copy the same tokens, or almost the same tokens, but the estimates of the probability of those tokens are different.
Okay.
So these are soft measures. So we also compared things like, other more hard estimates of diversity like cross blue or crossword error. So we have hypotheses generated by individual models, and we look at the average blue or the average word error between the hypotheses of the models. And that actually turns out to be worse than these measures of uncertainty because they're hard. They make hard decisions. Well, these are soft. They're sensitive. They're much more sensitive to the nature of the probabilities we're getting. And this behavior is about the same, or even worse, for English to French translation, French to English translation, German to English translation. So we tried four. So in the paper we tried English French, English German, French English, French German English, and this is consistent behavior. And the behavior is also consistent when you do teacher forcing. So here I am assessing uncertainty based on the beam search hypothesis, the one best beam search hypothesis. But if you do teacher forcing, if you have the original references and like if you feed certain things to the source and the target encoded to both the decoder, if you control the context of the decoder and the encoder, you have very similar behavior. So if you give it the input language as the input to the decoder, so the source input language to the target input language, then it's very confident in his predictions. So this is interesting behavior. This is behavior which does not occur in standard regression and classification models, and this is an example of like where things get really interesting when you start going to structured data. You get more interesting effects, and the benefits of decomposition of uncertainty is much bigger here. It's much more useful to decompose uncertainties for structured models, especially structured models and tasks which have a high natural data uncertainty level. So translation is a high data uncertainty task because multiple valid translations of the same input. Speech recognition, as you've seen here, is much less valuable to decompose uncertainties because it has a much lower amount of data uncertainty in the target. So this is nice. Yes?
Could you explain one more time why if our model was trained to translate from Russian to German, why it
Sorry, no. Sorry, it was trained to translate from English to German.
Okay, from English to German.
But we give it French because, so there's a hypothesis that because we're training on somewhat noisy data, we have sometimes in the training data we have examples of the same sentence in source and target. And it's really easy to just copy. So it has examples where it copies through. In fact, so the training data for English-French is 10 times bigger than for English-German. And the copy-through behavior is much crazier. So here we have Rocco 35, 33, and 20, and 20. For English-French, it's like 6 and 5. Sorry, I mean, obviously for the English-French model, I gave it German. Sorry, for the English-French model, I fed it French to the input and German to
So
the
it's
input.
different ones.
No, sorry, right now I'm talking about a different model, which I'm not showing here. Sorry.
This was what I was asking you.
Sorry? No, sorry, this is completely consistent. I'm talking about numbers from a different part of the table, for a different model with a different comparison.
The question is, you feed the French as a target language, and
No, as a source language.
as a source, yes, as a source language. And for what target language the model was trained? For French or for?
For German.
So
And we still
how it can copy from French to German? You said that
Because the BPE vocabulary is flexible enough.
what is BP?
What's BP?
Byte pair encoding. It's a subword, so it's like syllables, but not syllables. You can take words. So because the word vocabulary is just vast, but the amount of subword units is much smaller, you can dynamically learn a subword vocabulary of subword graphemic units called byte pair encoding.
If you were trained to translate English input to German,
Yeah?
and now you get French input, how could you be confident about copying French? It seems to be into French.
It's,
Well, in German.
so there's a hypothesis that there might be examples of parallel, like same text. So source and target text is the same in the training data. So there's examples of copying, which the model sees and the model learns to do. Right?
But how can they appear in the English-German text?
Right. So as in somebody gave just English. So English-German training data has English
So
somewhere.
noise in the training data.
Yes, there's noise in the training data. And because of the noise in the training data, there's maybe German or English. It learns that you can copy, and copying is really easy. Because it's monotonic, and everything else is much simpler to copy than it is to actually decode. Because decoding is non-monotonic. If you look at two different parts of the sentence, maybe rearrange stuff, it's a complicated process. Copying is really simple. You just copy. It's a monotonic process.
The model makes a mistake, but it's confident about this mistake.
Yeah, so sometimes it decides that, okay, in this case, I'm just going to do some copying. There's also a theory that the training data is noisy enough to have maybe even different languages there. Because it's parliamentary. So again, noisy data. It has noise in the data. So, I mean, copy through hasn't been fully explained. There's some theories for why copy through exists. And sometimes if you increase beam width, copying can get even more aggressive.
But if your data uncertainty is so low, this means that each
No,
model.
so the predictive posterior is very confident, but the models are diverse.
The models are diverse.
In terms of
but each
probabilities.
particular model
Is
is
very
sure
yes.
about its prediction.
Yes.
And at the same time, you say that each model is trying to copy the input text.
Yes. So it's
But then why are they diverse?
because
If they all copy the
right.
input
Well,
text.
because they still can make mistakes in copying, so the copied text can still be like different. So the hypothesis can be different.
Yes, okay, I agree that there
Right.
can be some
But
minor relations.
right. But in this case, the hypothesis is still the same because we're decoding using the ensemble. We're decoding using the ensemble, so the hypothesis is identical. But all the models have very different. The hypothesis decoded by the ensemble will not be the hypothesis decoded by each model. So the hypothesis decoded by the ensemble is one which the models will disagree on probabilistically. They will have maybe very different estimates of the individual log scores of the hypothesis. There'll be much more diversity in the log scores.
Mhm.
Okay. I
And this copy through behavior is much worse on English-French because the English-French dataset is 10 times bigger. So when you have even more data, it does copying much more confidently. So here you have ROCO. So for copy through behavior, your knowledge your total uncertainty ROCO is like 33. But on the English-French model, when I feed it German, the ROCO is like 6. So it's even more confident in copy through when you have more training data. And the reason is that maybe you have more examples of copying.
And haven't you tried to check it?
Sorry, check what? Sorry, check
the
what?
amount of noise in the training data.
It's
the amount of duplicated text.
30. People have looked at it, but there's 36 million sentences. It's hard to look at all over.
But you can do something like, I don't know, bootstrap and.
Well, I mean, you can definitely like. I mean, you can typically go through.
Yes.
I mean, I think it's really easy to go and see if there's like matching, like if source equals target. I haven't looked at it. Actually should.
Also, I wonder whether this effect is similar in nature to the effect that we observe in some likelihood-based generative models for like images. Because when you take a likelihood-based generative model and train it, for example, on cipher on image data and try to estimate the likelihood of, for example, like L-SAN images, stuff like that, you somehow you may obtain higher likelihood.
Oh yeah. So interesting. It may be related. It actually may be related. Maybe copying is a sub manifold. I mean, so the question is, it's much easier to think about it's much easier to think about the manifold in which images lie. Much more difficult to think about the manifold of text, because it'll have some tree-based weird structure. Anyways, but still pretty cool. So again, this is an initial work. And we still need to do some more ablation studies and stuff like that. But I think the cool stuff is that there's some interesting new effects we've uncovered, and I think we really show that the benefit of decomposing your uncertainties. So a lot of people said, no, this decomposition of uncertainties isn't that useful. Just look at the predictor posterior; it has everything you need. Well, it doesn't. So yeah, and this is the end. So uncertainties, philosophically important, is also practically useful. Ensembles are the theoretically motivated, correct way to estimate your uncertainty and separate out your measures, separate out your sources of uncertainty. Ensembles are expensive, so you can do ensemble distribution distillation, and we've shown that you can also do ensembles of auto-regressive models, which can be easily applied to sequence and token level error detection, sequence level OOD detection. There's some really cool new effects you haven't observed for classical models. Which are interesting, and I think it's an interesting area to explore. So yeah, that's it.
Okay.
Thank you.
Any questions?
More philosophical questions? Yes.
No, not really.
Fine. Whatever. Any questions?
The question about the entropy estimation you used, like quite simple.
Oh yeah. I did this.
Haven't
Right.
you tried something more complicated?
But this works so well, and it's so simple. I mean, so I tried looking at log score. So I tried. Fine. I'll do what I promised not to do, but I'll do it on the board. Terrible. So you can look at. So you have your. It doesn't write. Is this right? So you can look at a particular hypothesis, right? You can't see it? No. Fine. Never mind. I'm not gonna bother writing. Sorry.
Like we are proud of
Constant problem here. with the
the
markers.
university.
By the way, I have some.
Fine. I can.
I forgot to take out.
I-
At some point you always carry.
I can just show it on the paper on archive.
No, I have even two.
Oh. Ooh.
The red one and the green one.
This one seems to be mine.
Just like lightsabers, red and green.
Seems to be mine.
Yes, it's yours.
So, can you see this?
Also yours.
Yes, question.
So let's say we have a hypothesis. One. So this is not random development. This is a hypothesis. This is a realization of a this is some sentence we've translated. We can look at the negative log of p of y given x and d, right? Obviously normalized by sentence length. So this is the this is just the length normalized log probability of this sentence, right? Simple. We can use that as a measure of uncertainty. We can also use minus 1 over m L log sum log p y given x and theta m. We can also use the average log probability of all the models, right? This will be an estimate of data uncertainty, because each single model estimates only data uncertainty, average data uncertainty across models, across, see, m, right? Simple. And we can also look at the difference. And this difference will actually be less than 0. So if we look at, let's say, 1 over L log y given x and d minus 1 over m log plus minus y x given x and theta m sum over m. This will be less than or equal to 0 by Jensen. This is, but again, this will be 0 when the log predicted posterior and when the average log probability under all models is the same, and less than 0 when our models are diverse. So another measure of diversity, which is now no longer approximate, this is exact, but based on this particular hypothesis. We don't have any other like entropies along the hypothesis. This is just the log probabilities of the tokens we have predicted. And you can measure uncertainty using that approach as well, and it sometimes does a bit worse, sometimes a bit better than the entropy-based ones. So this is also in the paper, and it's also sort of motivated in the paper. And it's another way of doing it. But yeah, so the measures of uncertainty are crude, but they sort of work. The question is, I don't think you can get a better entropy-based one, because you need to somehow go along the path. But maybe you can consider deriving measures of uncertainty from different hypotheses within your beam. If you do beam search decoding, you have a beam width of 5. You can try to derive measures of uncertainty from the multiple different hypotheses, from your 1, 2nd, 3rd, and 4th, maybe 5th best hypothesis in your beam, and just something from that. That might be nice. Maybe you can look at beam stability. I don't know. It's an unexplored area. So yeah. Any other questions? No?
If not, then let us thank the speaker for
Cool.
very interesting talk.